this video, I'm going to show you how to do a time-based procedure for calculating the settlement beneath a uniformly loaded area, including the effects of secondary compression. So when we use Terzagh's one-dimensional consolidation theory, it assumes that there's no secondary compression, and so we can use that method to estimate settlement, but we have to do some adjustments to add in the secondary compression. So first I'll talk about some assumptions here, and I'll mention there are multiple ways of adding secondary compression. This is just one way, and you have to know the assumptions we're using here so you can assess whether that's reasonable for a particular problem. So our first assumption is that hypothesis A is correct. That means that the end of primary consolidation line is unique in E log sigma V prime space, and that the basically the amount of settlement due to secondary compression that happens during consolidation is the same for a thin layer and for a thick layer. Therefore, the shape of the settlement versus time curve is the same. It just has to be scaled for time to account for the different drainage path length. We're also going to assume that, zoom out a little bit here, there we go, that C alpha is a constant. So the coefficient of secondary compression is a constant that does not depend on things like time. It's going to be the same regardless of time. Layer thickness and the load increment ratio, or LIR, where load increment ratio is delta sigma V divided by sigma V naught prime. So in a traditional laboratory odometer test, we usually double the load each time. That means that delta sigma V is equal to sigma V naught prime. Therefore, the load increment ratio is usually 1 for a typical laboratory odometer test. In the field, it could be something much different, right? Maybe we're not doubling the load, maybe we're adding a smaller increment or something like that. So we're assuming that C alpha that we measure from the lab, generally with load increment ratio of 1, is going to be equal to C alpha that we get in the field for a different load increment ratio. So let's go through the steps here, walk you through, I think, 8 steps to get this done. The first step is that you have to pick a load stage from the laboratory test that best matches the field conditions that you're going to be analyzing, right? We want to pick the most representative load stage so that some of these assumptions are a little bit more tolerable, right? If you pick the wrong load stage, maybe C alpha would be really far off from what will happen in the field. But if you pick a load stage that's reasonably representative, you know, it should be better. All right, then the next step is you plot E versus log time from that load stage, right? We're still talking about the laboratory specimen here. And, sorry, I'm missing a axis label. This is void ratio versus log time. And so these data points represent measurements that you might make in the lab, and then you can sketch a line through that. And if we're plotting void ratio versus log time, when we reach secondary compression, the slope will be C alpha. So you can get that C alpha value from this plot. You can also get the void ratio at the end of primary consolidation. So at TP, that's associated with a corresponding void ratio EP. Then in the next step 3, we can compute C alpha epsilon. It's just C alpha divided by 1 plus EP. And this is important because it gives us secondary compression in terms of strain instead of in terms of void ratio. And when we go to settlement, we need to integrate strain. So C alpha epsilon is the constant that we want to use when we translate results from the laboratory to the field. Okay, then the next step 4 is to compute the ultimate amount of consolidation, SC ult, for the field loading condition. So basically, you know what the loading condition in the field is going to be. You have some sort of vertical load applied to a compressible soil layer, delta sigma V here. And then we know how to do this. We take the compressible layer and divide it into thin sublayers. If we're doing a spreadsheet solution, usually we're doing 8 to 10 sublayers. As you add more sublayers, the solution becomes more accurate. But usually 8 to 10 is good for most problems. And here I'm going to point out that the full thickness of the clay layer is H sub 0 or H naught, whereas the drainage path length is half of the layer thickness in this case because we have permeable layers at the top and bottom, so it's double drained. So H sub dr is the drainage path length, whereas H naught is the full layer thickness. Okay, we need both of those parameters here because HDR controls rate of consolidation, whereas H naught controls like the ultimate amount of consolidation that will happen. So we need both. Okay, step 5 is something you should be familiar with from your soil mechanics class, but I'm going to walk through it in some detail here so that you know how to do this. What we're going to get now is a plot of consolidation settlement versus time using Terzaghis one-dimensional consolidation theory. So to do that, we create an array of average degree of consolidation values and compute the corresponding time factor values that go with it. So for example, here I've put 0.1, 0.2, 0.3 for U average. And then we can calculate time factors using either the equations by Casagrande and Taylor or using the Fourier series expansion solution with a suitable number of terms. The equations by Casagrande and Taylor are way easier. I'd recommend that. Especially if you're doing this in Excel, where summation can be pretty complicated. Okay, so we have U average and T, and you would keep this going. Maybe U average would go up to 0.95 or something like that. You can't put a 1 in here. If you put 100% degree of consolidation, the time factor is infinity, so it won't work. You won't be able to calculate it. So you can go close to 1, but not all the way to 1. Then what we do, these are dimensionless parameters, right? So we have to go to dimensional parameters, consolidation, settlement, and time. And to get consolidation settlement, it's really easy. You just take the average degree of consolidation and multiply it by the ultimate consolidation settlement. So I haven't plugged in numbers here, I'm just leaving them as dots, but you can see how to quickly do that calculation. And then from our definition of time factor, you can see up here time factor is C sub V time divided by drainage path length squared. We can now compute time, right? We know the time factor and we know the drainage path length, and we have to have picked a C sub V value, right? So we need to know what CV we're using. Again, you would probably pick the CV from the load stage in the laboratory that best represents your field condition and plug that in here. And now you can compute time, right? So we've got what we want, which is settlement and time. Okay, now the next step is to plot those two things versus each other. So we have settlement on the y-axis, and usually we plot it to where these values are positive, but the axis is reversed, so they're descending, right? So if settlement's positive, that means the ground surface has gone down. Sometimes students will put negative numbers here, and the settlement will be going negative. I don't recommend doing that. It's easy to reverse the axes using any plotting software. So keep them positive, but just plot them positive going down. So this might be 0, and this might be, 0.2 meters or something like that down here. And then we have time on a log scale. So these would actually be arithmetic numbers appearing on the axis, but we transform the axis to log coordinates. I like that better than actually taking the log of the time values and plotting the logarithm of the time on a linear scale, because it's hard to interpret, for me, logarithms in my head. I like to see the actual numbers there. Okay, so we've plotted all the points that we had from our table up here, and then we can sketch a line through it. And then I'm asking you to draw 2 lines here. One is a horizontal line at SC ultimate, and your curve should asymptotically approach this horizontal line because Terzaghis one-dimensional consolidation solution does that, right? As time goes to infinity, U average goes to 1, therefore you'll ultimately get SC ult at time equals infinity. Then the second line, pick the inflection point. Basically, that's the point where the curvature changes from being concave down to concave up in this curve. It's also the point where you get the maximum slope in the settlement versus log time plot, and then just sketch a line tangent to that inflection point, right? So this is kind of like what we do using Casagrande's method for finding TP from a laboratory curve. We're just kind of doing it in reverse now, but the same principle applies. Okay, then in the next step, what we're going to do is incorporate secondary compression. So I've grayed out the curve that we got from step 6, just so you can see like this black line is what we're doing now in this step. What we're going to do is find the intersection of that line that goes through the inflection point and the horizontal line at SC ult. We're going to draw a line that has a slope of H naught times C alpha epsilon starting at that point. And it'll just go down constant at that slope because we're assuming C alpha is constant, therefore C alpha epsilon is constant too. Okay, and the reason why we're doing H naught, which is the full layer thickness, times C alpha epsilon here, is that we're plotting settlement on the y-axis. Okay, it's important to keep in mind what we're plotting on the y-axis to know what constant to put here on this slope. A common mistake students will use is that they'll forget the H naught and just plot C alpha epsilon. That would be correct if we were plotting strain here, right? If we're plotting vertical strain, you would just want C alpha epsilon because that's its definition. It's the slope of that line in strain versus log time space. If you were plotting void ratio, then you would put C alpha. We're not plotting either of those things. We're plotting settlement, and settlement is the integral of vertical strain over height. So H naught times C alpha epsilon is the settlement for this case, right? So we start at that point, draw the line at that slope, and you can see that, you know, our field curve from step 6 goes asymptotic to a horizontal line. This line is now lower than that to incorporate secondary compression. Then the 8th step, we fill in the settlement curve using judgment, right? So here we have this gray curve from Terzagh's one-dimensional consolidation solution. Now we have this line that we just did in step 7 that's also been grayed out. And we're just going to kind of fill that in with this black line using judgment. And to be consistent with assumption or hypothesis A, our black line should really follow Terzagh's one-dimensional consolidation solution as long as possible, and then start deviating only when we get down close to the secondary compression region. So I've really closely followed the Terzaghi field curve and then started deviating just right here and then gone kind of like asymptotic to a new line that has a slope of H naught times C alpha epsilon instead of going asymptotic to a horizontal line. So pretty straightforward procedure if you wanted to incorporate the effects of secondary compression into your settlement calculation. This is kind of a fairly straightforward and simple way of getting that done.